So for today, the agenda, let me go ahead and post the agenda so you can see what we have in store for today. Go ahead and put it in slideshow form. Whoops, there we go. So we are going to talk about the Moving Man lab that you turned in. This was our kind of our first report. It wasn't our first lab grade, but our first report. And we're going to have our next lab grade assigned today. It won't be a report though. It'll just be more of a worksheet kind of thing. It just goes in the lab category. But I'm going to talk a little bit about that. I'm going to talk about the corrections that you can make that are due next Monday. And you'll have a little bit of time in groups today as you're presenting or preparing for your presentation of the worksheet 1. Each group will have a certain question. And I'm just going to put you in your Moving Man lab groups so that you can also talk about how and if and why, or you're going to do corrections. I guess maybe not why, but whether or not you are and how. And then we are going to, in those groups, also give you a chance to check over the worksheet together and prepare to present your findings to the class. And then if we have time, I'm going to start the notes on vectors. And if not, we didn't have time first period, but if not, we'll do that on Thursday. And reminders, after we're done with class today, you will have seen all the answers for worksheet 1 from unit 4. And you will hopefully have corrected anything you may have missed or just verified that you had it all correct to begin with. And you'll submit that to Axis for a completion assignment. Basically, it's kind of completion / participation because you will have seen it all today by the end of the class. And then your new assignment will be to complete the PhET simulation of projectile motion and vectors, which is on Axis in topics for unit 4. This will not have a report this time, so you won't be working in groups, although I don't mind if you work together, but you won't be assigned into groups and you won't be completing it as a group. You'll be completing it individually, but it's an assignment, so you're more than welcome to work together if you choose to. But you won't need to be making a report. You won't be doing anything on OneNote. It's just going to be like a worksheet. So, and it's an inquiry kind of a thing where I haven't necessarily given you the notes on this. I want you to see if you can figure it out. Kind of, it walks you through it pretty step by step. I think it's one of the better activities I've seen. And I found it a few years ago and kind of edited it a little bit to make it fit what I like. And so I think it's going to be a good introduction to the concepts of how we're going to be using vectors to solve projectile motion. So that'll be due Thursday. In class Thursday, though, we will take some time to discuss it, to answer questions. Might even put you in groups for a few minutes to sort of compare answers and see if you're on the right track. And then it won't be due until after class that night, just as normal, the 11:59 normal deadline. But you'll have a chance, if you do get stuck or need some help, you will have some time Thursday to ask some questions about it. And so that's the agenda for today. If you happen to get, your internet gets blown out with all the high winds we've got going on, or they shut down your power today, but I know they're going to have some rolling outages due to the winds. So if that happens, now you know what we're doing in class and what the assignment is. And just a very brief comment on the test from Unit 3. I haven't graded all of them yet. I've graded a pretty good chunk of them though. And from what I've noticed, I haven't posted the grades yet. So I'm waiting till I get the curve figured out so I can put the curved things into the comments. But from what I've seen so far, it seems to be kind of the typical, what we're going to start to see probably from now until the end of the year in test grades. There's a good group of students who are in the 80s and 90s% range before the curve. And then there's some students that are 60 and below % before the curve. And then there's not very many between 60 and 80. What it ends up usually being at this point, and kind of from this point forward, is when the test rolls around, you either really get it and you're really ready for it and you really understand it well. So you score in that 80s and 90s range, or there's still some either misunderstanding or some missing pieces. Maybe you didn't have time to prepare real thoroughly. It could be a lot of reasons, and that usually ends up meaning you fall pretty low on the scale. And that's why we always have a retake. So just a reminder that in case I do post these grades before we meet again on Thursday, and you see it, if you scored really well, congratulations. If you didn't score very well, don't panic. You have a chance to do a retake, and all of you will have the opportunity to do corrections again. We'll probably do some of the corrections together in class. That might start Thursday, but more likely will be next Monday, because next Monday will be the main time frame when we're doing corrections and taking retakes. because the Monday after that, 2 weeks from today, we're taking the test on this unit. So this is a very short unit. So we want to try to get all the corrections and retakes done next week. But we might get a little start on it Thursday, but probably mostly starting next Monday on that. And the corrections will earn you the curve. So when I do post the grades, I'll put the non-curved grade in, but in the comments, it'll show you what your grade will be once you complete the corrections. So, all right. So any questions about the agenda or otherwise before we just jump right into talking about the lab and the how to do the lab corrections? All right. So here is how I would like you to do the lab corrections, and you can coordinate this with your group when you're together in breakouts in a little bit. Don't delete or change anything that's already there. Just leave it the way it is and add to it. Okay, so even if something's wrong, if you're just missing something, add to it and either make it a different colored font like blue or green or purple, something that stands out. Or use the highlighter and just make it whatever color font you want, but run the highlighter over it so it stands out. So if you're just missing something like titles or labels or units or something like that, just use a different colored font or highlight it and just add it in. If you had something that was wrong, like maybe one of your graphs was wrong, or you didn't do the sequence for the velocity time part or something like that, then you don't take away what you did before, leave everything there originally so I can compare the original to the new, and then just add the new off to the side or down at the bottom or something. Okay, so if you have to completely replace something, don't delete the old stuff. Leave the old stuff there and just add the new stuff down and just highlight that this is the corrected form. Because you'll see my notes in red. So I would prefer if you use a different color besides red, so I can see my comments in red and your corrections in some other color. But don't delete anything. Normally, if we were on campus, I would actually be collecting your lab journals, and in those journals, I wouldn't want you to be erasing things. I would want you to just be adding in your corrections, and I want you to take that same philosophy here. So don't delete anything, don't erase anything, just add in corrections to your lab report. And as the classroom management plan says, I know it's been a while since we looked at that and you may have forgotten, you earn back half of the points that you missed if you do all the corrections. So if everything that I commented on and showed why I took off points in my red comments, if you correct all of those things, then you will earn back half of the points you missed. So if you had a 45 out of 50, your final score would be a 47.5. And if you had a 40 out of 50, your final score would be a 45. So you'll just earn half of the points you missed. In this classroom management plan, it does say that you can't normally earn points back on the data section, but in the rubric, I didn't really organize the rubric that way this year because it's a simulation and we're doing it all online. So for this one, you can just earn points back, no limitations. So if you miss something, you can earn half back. Okay, so there's no limitation since it's not a traditional handwritten lab report. And we didn't actually collect real data, we just did a simulation. So any questions about how to do the corrections for lab? You just need to have those done by next Monday. If you get them done sooner, somebody in your group can just shoot me an email and just say, hey, Mr. Webb, our group finished the corrections. And then at some point I'll go in and change the grade. I'll make a note in Access and change the grade for your group members. All right, so now let's talk a little bit about the lab. So I want to highlight a few things here. In your conclusion, this is what I was hoping you would recognize, and most of you did actually. And I had a chance to talk with a lot of groups and sort of briefly discuss this before, but if you didn't catch it before, I want to get one more pass at it to make sure it's really sinking in. This is actual data from one of the groups. I don't remember which class it was. As I was grading them, I saw some graphs. I said, I'm going to paste these in as examples of ones that would earn full credit. They're not, the things that I'm going to show you aren't necessarily always the #1 best one I saw. It was just, oh, this one earns full credit. Let me just copy and paste some of these in. So some of you might have had things that are a little neater, a little more organized or whatever, but everything I show you today would earn full credit. And I just want you to see the patterns and the things I'm looking for. So this is the data from one of the groups, and I thought it followed the pattern nicely. It was well represented. And here's what I want you to see from their models. Their position time graph, they had to square time to linearize it. and their slope had units meters per second squared, which is acceleration. The velocity time graph did not have to be linearized. It was already linear, and their slope had meters per second squared as the unit, also acceleration. And then their velocity position graph, they had to square the velocity to linearize it. And again, the slope ended up, after they linearized it, being in meters per second squared. So you can see the units for every slope were meters per second squared, but the numbers were not the same numbers. Now, this up here, I just wrote that group, that I took the data from one group, and that group chose for their simulation an acceleration of 1.2 meters per second. And you'll notice that almost identically matches the slope of their velocity time graph. And that's not a coincidence. That's actually what you should see if your data is solid. So here is the second kinematics equation we learned. Over here on the right in green is the way it's traditionally written by College Board. And in the left, I've rearranged it a bit. I've subtracted the initial position to the other side to get a delta x. And then I've put the 1/2 AT squared first and the VOT last. That's all I've done, just a couple simple algebra steps. But what you'll hopefully notice is delta x is position, time is squared, just like this. And it tells me if I write it this way, my slope should be half the acceleration. And their acceleration is 1.2. And the slope of the position time versus time squared graph is about half of that. So it shows that same pattern. The second kinematics equation, the first one we learned, but the second one here on the slide, is the VVAT equation, the very first one we learned. And I just rearranged, I put AT in front of VO. So when you do that, you'll notice this is velocity versus time, just like this model up here. And the slope is the acceleration, and that's what they found. Their slope of this graph matched the acceleration they set the simulation to. The third kinematics equation we learned is over here in green, with the way College Board traditionally writes it. And all I've done is instead of writing xf minus xo, I've changed that to delta x, and I put the 2a delta x in front and the VO squared in the back or the end. So just kind of done a couple simple algebra steps. But now you can see this is velocity squared, just like this model, versus position, just like this model. And the slope is twice the acceleration, which is about what they found. So their models, all three of them, mimic the three kinematics equations, showing that if you linearize position and time, you have to square the time. If you linearize velocity and position, you have to square the velocity. And the velocity time graph is already linear. And the slopes of those graphs should follow the pattern indicated in these kinematics equations based on how the acceleration value is modified by the constants. So in the second example here, there's no constant, it's just the acceleration. But in the first one, there's a constant of 1/2. And in the third one, there's a constant of 2. And so we see that following through in the pattern here. So that's what I was hoping you would notice in the conclusion. Most of you did, but for those that maybe didn't quite see it the first time around, I wanted to make sure we discussed it. Any questions about the pattern here? All right, now I want to just show you, and again, some of these graphs and diagrams I'm going to show you weren't necessarily what I would consider the prettiest or the best. I picked ones that earned full credit just to show you an example of a few. And I don't even remember which class I picked them from. I just copied a bunch and pasted in. But I wanted to highlight a few things. So in this first graph here, position versus time graph. So they've got a title, they've got the graph, which looks quadratic in nature, parabolic in shape, that fits. It's position on the y-axis in meters, it's time on the x-axis in seconds. Everything looks like it should. Like I said, some other groups made it neater and made it fancier, but this is fine. This has everything that's needed. Title, axes, units, we're good to go. Position versus time squared. So this is the linearized model, and they squared the time to linearize it, and they've shown that now the x-axis is time squared and the units are now seconds squared. They got their title down here. Whether the title is below or above, I'm not picky on where it is, just needs a title. And then the axis, they just kind of hand wrote them in with the editing tool. Some people did nice fancy typing them in and all kinds of stuff. Either way is fine, it just has to be there. All right, and then in terms of finding the sequence for the velocity time data, I liked that this group, and this is I think why I mainly chose their graphs, I like that they were one of the few groups that actually drew the sequence in. Wasn't required, kind of an extra step, but I like the fact that they drew the sequence in here. So they've got one going from 0 up to 10 seconds. They've got one going from 0 to 8 seconds, one from 0 to 6 seconds, one from 0 to 4, and one from 0 to 2. They actually showed me which sequence they used. So this one that goes from 0 to 10, the slope of that would tell me the average velocity from 0 to 10. But it would also tell me the instantaneous velocity at the midpoint, which would be 5 seconds. This black line goes from 0 seconds to 8 seconds. The slope would tell me the average velocity from 0 to 8 seconds. But it would also tell me the instantaneous velocity at the midpoint, 4. So this was a nice visual for how they showed the way they found their velocities. Now down here in this one, whoops, this where it says number 6 and has a table with some work shown, this group didn't do a graphical approach. They just did it purely mathematical, but I thought it was really well organized and showed me that they were using sequence. So they said, here we found the time at 0.5 seconds, which matches the table here. They took the time at 1 second minus the time at 0 seconds, divided by 1 minus 0, because that was the difference in time from 1 to 0. And so that ended up being 0.495 divided by 1. They were pretty clever here. All of their time frames to get these midpoints, they always used a 1 second increment. So to get half a second time frame for their instantaneous, they chose 1 and 0 to make it a 1 second interval. To get the 1.5 instantaneous, they chose 2 and 1 to make it a 1 second interval. They just made it easier on themselves for the math. Every interval they chose was 1 second. Thought it was a really clever approach. And it clearly shows me that they were using sequence. They weren't just taking numbers off the simulation, which was part of the requirement. You had to use sequence. Said that in the directions. So this is another way to show it. If you didn't show it visually, you could show it mathematically. And then their velocity versus time graph was already linear. They got a title, they got the units, they got the axes labeled, and just showing you basically the things that I was looking for, traditional things you need on a graph, title and axes. And then, like the direction said, you had to use sequence. So somehow you had to show me how you did that so I could track your information. So as you look through, you'll see my comments in red. You've seen a few examples. I do want to show you one in Teams, actually. And again, this, I don't even know if I would say this is necessarily the best, but it was very good. And I just want you to see one. I think this one earned full points, if I remember right. So a couple things about it that stood out to me. One, it was very neat and very consistent. So here is point number 1 on the rubric. They've got their table, they've got titles and units, they've got their starting information, very nice and orderly. Number 2 on the rubric, they've got their title, their units, they've got the graph. Number 3 on the rubric, their data table. Number 4, the linearized, they've got titles, they've got units. Everything is just very thorough, very organized. Here they've shown how they calculated the sequence. They got their mathematical models. So yeah, very organized. Everything's numbered. That just follows right along with the rubric to make it really clear what everything is. So I thought this was very nicely done. And if I remember correctly, this is one of the groups that earned full credit. I don't think they had anything missing at all. I don't see any red font for me. So I think this was a perfect score. So just so you can see an example of the kinds of things that might make it nice and orderly. And I think the more organized it is, not only the better it helps me when I'm grading it, but because I'm not going to miss things that you may have there, I can follow the train of thought. But it also, I think, makes it easier for the group when you're working. If number 1 is here, number 2 is here, and you've divided up who's doing which parts, it's really clear where everything's at, and it's all numbered, so you're not confused on. I had some groups that had like multiple copies of the same information because I think of just the lack of organization, lack of communication in the group. If you had too much information, that you didn't get discounted or deducted points, but it just meant you weren't efficient with your time. So just a few things there to kind of help you understand what I'm looking for, what kinds of things might help as you work on your lab and do the corrections. Questions on anything about the lab, the Moving Man lab? All right, so corrections are due by next Monday at 11:59. It's always going to be that 11:59 deadline unless I say specifically otherwise, and I'll make it really clear if it's not. So by Monday night, those have to be done. You earn half the points back of anything you missed that you do correct. All right, so today for the next section, we are going to take about 20 minutes, and I'm going to have you in your breakout groups, same groups that you were in lab with, so that you can talk about how and when and if you're going to do corrections. So I'll give you some time to do that. Your two priorities should be talk about the lab, decide if you're going to do corrections, and if you are, how you're going to do them, who's going to do which parts. Are you going to meet together? Are you just going to assign who does what? So that's one of your priorities in this time, this 20 minutes. The second priority is for you to work on, well, you can check the whole worksheet one, but one of the questions your group is going to teach. So group one is going to teach question one, just keeping it pretty simple here. Group two, going to teach question two. Group three is going to teach question three. And group four, this is where it switches a bit. Group four, you're going to teach question five. I will teach question four. Okay, so I've italicized that to draw some attention to it. Any questions? All right, so your priority should be talk about the lab, how and if you're going to do corrections, talk about the question that you were assigned. When you do your presentation to the class, I want you to do it as if you're teaching the class. I don't want it to all be verbal. You need to use some visual, and I would very much prefer you not just try to hold your paper to the camera. So find a way to snapshot it, screen share it, whiteboard it, something, okay? And I'll go ahead and put you into your groups. So group one, I got my list here. Jack, Andy, and Ethan. Group two, Kayla, Nick, Sally, and Cade. Kayla, Sally. Group three, Kyle, Rocky, Aiden. Rocky's not here. Okay. And group four, Evan, Johnny, and Nat. Just making sure it all came through. Yep. All right, off you go. Let me know if you have questions. You can call me into your breakout rooms. All right, it looks like everybody's back from the breakout rooms. So we'll have each group just take a few minutes and present the answers to your problem, the question you were assigned. Like I said, use screen share, whatever works for your group to show your work and explain it. And let's start off with group one and problem one.
I'll do Andy's first too.
Okay. Hopefully he'll join us again.
Yeah. So yeah, we can. I think everyone can, right?
Yeah.
Okay, cool. So for the first one, it's just a diagram showing the ball is going in a negative direction. We specified the directions on both axes, and that the initial velocity or the initial speed is 20 meters per second, but it's going down, so negative. The second one, we just did -10 because it's due to gravity, so we just rounded it to make it easier. And then for C, you're just doing, I think, VVAT. Or sorry, that is, I think that's
the second kinematics equation.
Yeah, this is second kinematic. So then you're just gonna plug in all your values, and then you got -20 meters per second times 4 seconds plus 1/2 times -10 times 4 squared. And that comes out to -80 meters minus -80 meters, which you get -160. And then this one is just VVAT, so you plug your values in again, and then you get 5 equals negative, or 5 equals 2 plus t, and if you just do some basic math, you'll get t equals 3 seconds.
All right, and E and F were a little bit more challenging, but E, we used the second kinematics equation again, and we plugged in all our values, this time with -300 meters. I have a point there, it's just hard to see. So -300 meters, and then all of the other values, and then you arrange it so that you have a constant over, or not a constant, like a one of your variables over s squared times t squared, or second squared times t squared, and then seconds and just t, and then no seconds or t. And then you can factor that. I didn't factor it like normal because it's 300 and I didn't want to think that hard. So I put it in the quadratic formula, and you get negative 10 seconds or positive 6 seconds. But negative 10 doesn't make any sense, so it's got to be positive 6 seconds. And then for the final one, we did, this one is the third kinematics equation. And so we put in negative 20 meters per second, negative 10 meters per second squared, and then negative 100 meters for the value that they gave us. And then you do the algebra, and you have to square root 2400, which gives you very close to negative 49, or it gives you plus or minus 49 meters per second. Because it's speed, then it would just be normal or positive 49 meters per second, but we did velocity, so it's negative 49 meters per second. Yeah,
Good.
any questions?
Just a couple quick comments on F, for example. Speed and velocity, their College Board is very flexible with interchanging those words. They don't technically mean the same thing, but the speed in most scenarios is the magnitude or the number size of the velocity. So yeah, since they've left it as velocity and left it as negative 49 meters per second, they would still earn for full credit, even though it says calculate the speed, because they're not going to nitpick that much. For part E with the quadratic formula, if you didn't want to use the quadratic formula and you did want to try to factor it, you could factor out the -5, and then you just get t squared plus 4t minus 60, and then you can factor the 60 pretty easy. So that's not too bad if you don't remember the quadratic formula. Also, you could, if you have a CAS form of the TI Inspire, so if you use 9.8, then it's not going to be very easily factored. But if you use 10, you could factor it. But if you have a TI Inspire with the CAS on it, you can also use the solver function to solve for quadratic equations. So we might show that sometime. And then the last comment, here they've shown the substitution and then the algebra steps of how you go from the substitution to the final answer. What College Board will require, and no need to change it for this worksheet by any means, but for our tests and then for the exam, just one thing I want to keep teaching you about is what they're expecting. They do not expect you to show those algebra steps, but they do expect you to show the substitution, and they also would require that you show the original equation before you substitute. So like for F, just for example, I can clearly see which equation they used, but because they didn't show the equation, they would not get full credit. They would lose 1 point out of the possible points, probably. Most of the time, the rubric gives you 1 point for showing the equation itself, 1 point for doing the substitution, but they don't give you any points for these algebra steps in between. So if it helps you to do the algebra steps on paper, I highly recommend it, but those wouldn't earn you points, but you normally do need to put the equation in. All right, very nicely done though, clear work. Good explanations. Any questions? All right, group 2, question 2.
So on question 2, A, we have the diagram there, which shows that the rock is going in a positive direction at a speed of 15 meters per second. And B, we know the acceleration is negative 9.8 because that is gravity, and gravity is pulling it down, which is the negative direction.
And then for C, to calculate the displacement, we used the second kinematics equation, and we could plug in, we knew the initial velocity that they gave us, we knew the time, and we know the acceleration. So then simplified, we got positive 10.1 meters.
And then for D, we used VBAT, and then substitute, the final velocity is the 3 meters per second, the initial is 15 meters per second, and then acceleration of gravity, negative 9.8, and then solve for T, and we got 1.22 seconds. And then E, basically the same thing, VVAT, and then the final velocity is negative because it's downward speed of 5 meters per second. And then same thing, 15 for the initial, and then negative 9.8 for the acceleration. And then we got T equals 2.04 seconds.
Any questions? I didn't really pay too much attention to sig figs on page 1. I don't know if, I think they were probably right, or it might have stood out to me. Just for sig figs here, the numbers that are given all have 2, so we probably should be rounding. It looks like, yeah, rounding all our answers to show 2 sig figs. Sometimes College Board counts sig figs and sometimes they don't. So sometimes it's part of the rubric, sometimes it's not. In the question, they very rarely say whether it is or not. So I would just, if there is a numerical answer, I'd always try to round it to sig figs just in case it's part of the rubric. I have noticed in the last 5 years that they're grading that as part of the rubric less and less. It usually only shows up maybe 1 point out of all 5 free response questions combined. So it used to be on almost every question, but they're asking fewer and fewer free response questions with numbers. They're doing a lot more like that last question on your test, where you just have to come up with an equation. And obviously, if there's no numbers, there are no sig figs. So that's part of it. But okay, great job. Let's have group 3, question 3.
Oh, I'm scared sharing my screen real quick. So, or Aiden, I realize we.
Oh yeah.
messed a little
Okay,
bit.
so we have like the ball going up and then it goes down, and then we have the time right here. Since it's only half of the 3.8 seconds, it's only 1.9 seconds at the very top, and then it goes down for the other part of the seconds. And the displacement would be 0 because it just goes back down anyways, and it, yeah.
And also that final velocity at that halfway point is 0 because that's right between when it stops accelerating and before it starts or going back down. But then so we use the second kinematics equation to originally plug everything, or to use with acceleration and time before and then so we got the answer for how to find the initial acceleration with the change in distance, and then so we plug that in, which is 0. So it's just 70.76 over 1.9. So our initial velocity was 37.2 meters per second.
So quick comment. I think I may have confused you when I gave you 2 ways to do it. What you did here is correct, except in the time, if you look at your very first row there of your equation where it says delta x equals VO 1.9 plus 1/2 -9, if you're going to use the delta x as 0, which is one of the ways to do it and the way that you've explained here, then your time should be the full 3.8 seconds in both areas. So
okay.
it should be 3.8 squared and also 3.8 beside the VO.
Oh, so then this is this is what we originally did. I thought
Yeah,
so then we originally had it right. Okay.
Yeah.
That's my bad.
Yeah, no problem. So yeah, this is correct. What I was saying is, if you think about going to the peak, then you could just use VVAT, the first equation.
Okay.
Because the time would be 1.9 to the top, and at the top, the final velocity would be 0. So if you're using the second one like you did, then this is exactly correct. If you're using the first kinematics equation, then you would have to do half the time and use your final velocity as what it is at the top, and you could still find this same answer. So there's 2 routes to go.
Okay.
Yeah. So this is exactly correct. And if you go back to the previous one, looking at the very last step, VO equals 0 plus 70 points. The only difference is it should just be divided by 3.8, which gives you half of your answer. If you go back to the right one, that is half. So it was just that one small mistake.
Yeah.
But this one's perfectly right. This is exactly right here. So sorry I confused you. I was trying to give you another option and I got you confused.
No, you're good. Because we were already starting with like the second kinematics when we got that information, so it kind of tripped us up a little bit.
Yeah.
That was it.
All right, looks good. Any questions on number 3? All right, I've got number 4. Let me show you number 4 here. If I can find it. There we go. All right, so number 4, we got a rock thrown straight up with an initial speed of 22 meters per second. How long will it be in the air before it returns to the thrower? Graph the vertical position, velocity, and acceleration of the rock on the axes provided. So let's talk about that first. The position time is just going to look parabolic in shape because as time passes from left to right, the rock goes up and increases till it reaches its maximum height and then comes back down until it reaches its initial height. So it's just a parabola basically for the position times time. For velocity, not times time, but for position time graph. For the velocity time graph, it starts with its maximum positive velocity right when it's thrown, and gravity is going to slow it down and slow it down and slow it down till it reaches its peak, where its velocity will be 0 right at the peak. And then it's going to start falling and increasing in velocity, but now its velocities are negative, so it's increasing in its negative velocity as it falls back down. And then as they mentioned in the previous question, and a couple previous questions, the acceleration is constant because it's just due to gravity. And so it's just going to be constant at the -10 or -9.8 line value for acceleration. Then it says, make a well-labeled diagram of the situation. So the velocity is upward. I've chosen upward to be the positive direction. I know my final position is going to equal my initial position, but kind of, I think that's a Y. Yeah, it looks like it's trying to show me some grammatical. See if I can get it to ignore all of these. Maybe not since it's in a formula. Anyway, that velocity will be, maybe it's a velocity, I can't tell. If final velocity and initial velocity would be equal but opposite, that would make more sense than talking about position. So, and then in terms of listing the quantities, acceleration is due to gravity, so it's the -10. The change in position would be 0 because it starts at that certain height and ends at the same height. The initial velocity is 22 in the upward direction, and we're trying to find time. So I just used the second kinematics equation. I know my delta y, so here's my equation in this first part. Delta y equals 1/2 at squared plus vi delta t. I substitute 0 in for delta y, substitute -10 in for a, substitute 22 in for vi, and then I'm just solving for t. Since it's 0 over here, I just take half of the -10 to get -5 and then move it to the other side of the equation. Divide both sides by t, so then I end up getting 5 meters per second squared. T equals 22 meters per second. And if I divide both the 22 meters per second by the 5, I end up getting the time would be 4.4 seconds. So questions on number 4, graphs or math?
I did it differently, but I got the same answer.
Mhm.
I used VVAT for like each like half, like the first half and the second half, to find the time, and then I just like added them together. That's fine.
Yeah, that works fine too. You'll find as we get more and more into these problems, there's frequently multiple routes to go. So good. Anything else on number 4? All right, group 4, you've got question 5.
All right. So for 5A, or should I read the question?
Yeah, sure. Go ahead.
I used the third kinematics equation to find the final velocity. And then I used the final velocity to plug it into VVAT in order to get the time. I did that so I didn't have to deal with the quadratic of the second kinematics equation. Um, I don't know what else to say. Should I describe the?
No,
Well,
I think that's clear. We can see the work. It just give people time to absorb it a little bit.
okay. I guess for this part between these two steps, it was positive, but when I square rooted it, it became plus or minus. We took the negative one because it's falling downwards.
Okay, and then for B, like we used in the first part of the problem for question A, we use kinematics equation number 3, which is velocity final squared equals velocity initial squared plus 2a times change in x. And the missing variable here is time. So some of you might have gotten a different answer from us because we used negative 9.8 for the downward acceleration instead of 10. So some of you might have gotten a little bit of a different answer. And then we square rooted the velocity final squared at the end, which Nat is going to explain how we did that.
And then, so at the end, we got, since you can't square root a negative, it went into positive form. And so then we took the negative because it is falling downwards after doing so. And we got negative 49.5 meters per second.
Good. And when you use that third kinematics equation, because of the squared nature, you often do have to then think, just based on the context of the question, what the sign should be, because often when you're going to lose the negatives because you're squaring numbers. So yeah, that's kind of the downside of that one, is you really do have to think more conceptually about what the sign should be for your answer. But mathematically, it works nicely. I want to show you something, just again, kind of a test taking skill for AP. I can just say it, I guess I don't have to show you. On mine, I did the same thing that they did for part A. And so for part B, they've really already done that work in part A. And so you don't have to do the work again. If the way you solve B is something you use to do A, in part B, you can just give the answer and say, see work for part A. You don't have to rewrite it. And especially when you're in the pressure of the AP exam and trying to get a lot done, if that ever happens, I would strongly recommend that you do that, so you don't take the time to rewrite what you've already done in the previous step. You just have to say, here's the answer, see part A for the way that I solved it. And I did it this way for two reasons. Like Evan said, it avoids using the quadratic equation, having to use a quadratic formula or a solver function to get the answer, which isn't a big deal, but it's slightly easier. And also because I read part B and saw, oh, I'm going to have to find the velocity anyway, so I might as well just find it now, and then I can use it without having to use quadratic. So it kind of made the overall problem easier. And I was finding something, even though it made part A a two-step problem, one of the steps was answering part B. So just test taking strategy. Thank you. Any questions for that group? All right, thank you. So worksheet 1, then you just need to make sure you submit that on Access for tonight. And hopefully everything that we went over today helps make sure you understood it well. If you have questions, we got a few minutes here. We'll dismiss here in just about 2 minutes. You have a few minutes left over. If you have some questions, you can stick around and ask. But I do want to quickly show you about the assignment that I'm giving you today. I showed you in the agenda at the beginning of class, you're going to be doing the PhET on vectors and projectile motion. So let me go to Access and show you where to find it. So once you get to Access, you're going to go to Topics. And then we are now on Unit 4, Free Fall and Projectile Motion. And over here on the right, you can see Worksheet 1, which you've already just done. Right below that, PhET, Vectors, and Projectile Motion. So when you click on this, it takes you to the actual simulation. And in the directions, it tells you to go to the vectors part first. The directions are right below. So there's the link, and then right below PhET, PDF form, and doc form. So whichever form of the file you need. It is kind of long, and so one thing I'll say is a lot of it's just direction. So if it just says click the box that says acceleration vectors, you don't have to write anything there. It's just giving you directions. It's just when there's a question, and you do not need to answer the question in full sentences. So what is the direction of the vector? You can just say up or down. Like you don't have to say the direction of the vector is. You can make one-word answers if it only takes one word to answer it. Okay, so you don't have to write complete sentences. I want you to, this is designed to help you sort of process what you're seeing, process what you're experiencing, and sort of as an inquiry activity, learn about review vectors and learn about how it applies to projectile motion. So by no means do you need to write full sentences, okay? Because there's a lot of questions to answer. So if you can answer it in 1 or 2 or 3 words, that's fine. And if it doesn't have a question, sometimes it's just telling you to do something. But if it does have a question, make sure that you answer it. And if it says show your work, you do need to show your work, okay? But you do not need to use full sentences. All right. You will have some time on Thursday in class to work on this. So if you're not able to get it all done by Thursday, most times usually this has come up during freshman retreat. And so the freshmen had to do it on their own and the upperclassmen just did it in class. And most times a lot of students would get done or almost done in a 47-minute period. So I'm thinking that should be about the length of time it'll take you. And so I am going to give you some time Thursday because you don't have really much time today to work on it in class. So Thursday, you'll have some time to ask questions and also some class time to work on it. Any questions? It'll be due Thursday night. All right, so we've got about 4 minutes left. If you have any questions you want to ask, you're welcome to stick around and ask those questions. And if not, you're dismissed, and I hope you have a great day.
Thank you.
Thank you.